This is Larry Moore. I'd like to welcome you back to our biological wastewater treatment training series. Today we'll be doing presentation number 11, and we're going to focus on aeration systems because they are so important to biological wastewater treatment processes. Let's look first at our references. Again, I use Metcalf and Eddy 4th edition. I always call it my wastewater Bible. There's a lot of good practical information in the Metcalf and Eddy books. I've used them for almost 50 years now. They're very helpful. And then the Water Environment Federation Activated Sludge Process Control training module for operators. I've also used that in preparation of the slides for this presentation. So let's look at the outline. We're going to talk a little bit about energy use in wastewater treatment plants, especially related to the aeration systems. And then we'll talk about the two primary types of aeration system, diffused aeration systems. We'll talk about how we measure performance, of diffused aeration systems. And then we'll look at energy conservation measures in diffused air systems. Then we'll look at mechanical or surface aeration and talk about how we measure performance of surface aerators. And then we'll also look at energy conservation measures for surface aerators. So that's our outline. So let's talk a little bit about energy use in wastewater plants. Typically, the aeration system is going to consume about 25 to 60% of the total plant energy used. And more typically, the number will be about 50 to 60% of total plant energy use. We're talking conventional activated sludge. I would normally estimate that the aeration system would consume about 50% of the energy. And in an extended aeration activated sludge process would be about 60% of the total plant energy use. So we want them, as engineers, design aeration systems so that we supply the amount of oxygen that's needed by the process. And that's easier said than done. But aeration systems, they have to be flexible because the air required, can vary quite a bit. When we start up a treatment plant, it may be only operating at 20 or 25% of its design loading. So we need, again, flexibility in the aeration system to be able to supply that lower amount of oxygen because we're so far below the design capacity. So we'll talk more about how to do that later. So types of aeration systems, again, diffused aeration, mechanical surface aeration, those are our predominant types of aeration systems, but there are also some hybrid systems out there. We won't talk about them in our presentation, but jet systems, U-tube aeration systems, and submerged turbine aerators. So initially, let's talk about diffused aeration systems, and you can see the various parts of it: air intake system, blowers, the air piping system, diffusers, and then the controls that we use to control the aeration system. So all of these components are important, but arguably the blowers are the most important part, and we'll focus on the blowers. The blowers are essentially high volume, low pressure air compressors. So that's what we need to realize. This is a picture again of the biological reactor that's being aerated. And again, we know that the aeration system provides mixing to keep the biomass in intimate contact with the organics and nutrients in the raw wastewater. So mixing is important, but oxygen transfer is also very important. We need to be able to supply the oxygen that the biomass needs to break down the organic matter in the wastewater, to oxidize the nitrogen in the wastewater. And so we want to do that as efficiently as possible. So the configuration of the diffusers is very important. Again, the diffusers in a diffused air system, they're located typically about a foot off the bottom of the reactor. The air goes from the blower through the piping network into the diffusers, and the air is bubbled into the reactor contents as it comes out of diffusers. And we have porous diffusers and we have non-porous diffusers. The old terminology was, when we said porous diffusers, and the old terminology would say fine bubble diffusers. And then non-porous is comparable to saying coarse bubble diffusers. But again, the location of the diffusers along the length of the reactor is very important. And another thing we need to worry about is if we have fine bubble diffusers, we want to make sure that we don't provide too high an airflow rate across the diffusers, or we may actually produce coarse bubbles instead of fine bubbles, and that's going to reduce our oxygen transfer efficiency. Here's a picture of a typical non-porous diffuser, or what we used to call a coarse bubble diffuser. Typically, they're made of stainless steel. Another type of non-porous diffuser, again, made of stainless steel. And this is a picture of the diffusers in the aeration basins at the North or Stiles wastewater treatment plant in Memphis. Interestingly, these reactors are 430 feet long by 30 feet wide and about 14 feet deep. And so they are almost, not quite, but almost perfect plug flow reactors. And when these basins were constructed in the mid-1970s, the diffusers were laid out along the length of the reactor, and we had the same amount of diffusers at the front of the reactor as we do at the tail end of the reactor. So what we typically see in these aeration basins is maybe a DO concentration of 0.5 milligram per liter of less at the front end of the reactor, because that's where most of the oxygen demand is exerted. And then as we move through and we get to the tail end of the reactor, the DO concentration may be 3 or 4 milligrams per liter. So again, by providing the same amount of air along the length of the reactor, we're going to see changing DO concentrations throughout the reactor. Ceramic disc porous diffusers can be used and laid out at the bottom of the reactor. And again, these porous diffusers are going to provide about 50% greater oxygen transfer efficiency than non-porous diffusers. We have, we just saw the ceramic diffusers. One way to do it, ceramic diffusers, they are susceptible to clogging if we get particulates coming through in the air that's supplied to the diffusers. Ordinarily, again, we're going to have air filters that are going to filter out impurities in the air on the intake side of the blower, and hopefully we'll remove most of the particulates, but some particulates can get through and actually potentially cause plugging of these ceramic diffusers. Another type of porous diffuser is the flexible membrane diffusers. And again, these have membranes that provide flexibility. They can flex and would be less susceptible to plugging. So the membrane, porous membrane diffusers are very popular. And this gives you an idea of the kind of air bubbles that we generate with these type of diffusers. Again, this is a porous membrane diffusers, and you can see fine bubbles being generated by this system. Let's talk a little bit about blowers. Positive displacement blowers provide a fairly constant air flow rate over a wide range of discharge pressures. And positive displacement blowers are ideally suited for small municipal wastewater treatment plants. When I say small, I'm saying less than about 5 million gallons a day in design capacity. Then we have multi-stage centrifugal blowers. These blowers provide a wide range of flow rates over a fairly narrow range of discharge pressures. Multi-stage centrifugal blowers are used at small or large wastewater treatment plants. Then we have single-stage centrifugal blowers, and And again, they can be used at small or large wastewater treatment plants. Okay, let's talk about how we measure the performance of diffused aeration systems. When we talk about oxygen transfer capacity of diffused aeration systems, we do so in terms of percent transfer efficiency. So for a porous diffused air system, the standard oxygen transfer efficiency, which will be with tap water at 20 degrees C, initial DO concentration of 0.0 milligram per liter, and at sea level or 1 atmosphere of pressure. That's how we measure our aeration equipment at standard conditions. Well, at standard conditions, the oxygen transfer efficiency for porous diffused aeration system will be 10 to 15% typically. For a non-porous diffused air system, the standard oxygen transfer efficiency would be about 2/3 of what it is for a porous diffused air system. But then what we have to do is when we aerate, we have to design our system for field conditions. We're not treating tap water, wastewater. It's harder to get oxygen into the water than tap water. We're not always at 20 degrees C. We're typically trying to maintain a DO concentration of 1 to 2 milligrams per liter in the mixed liquor. And we're not always at sea level. So we have to calculate what the transfer efficiency will be at field conditions. And a ballpark estimate, again, a very ballpark estimate, if we're talking elevations less than about 1,000 feet, and trying to maintain a DO concentration of 1 to 2 milligrams per liter in the biological reactor, then a ballpark estimate is that the field oxygen transfer efficiency will be about 60% of the standard oxygen transfer efficiency. But again, in each application, we want to calculate the oxygen transfer efficiency more exactly rather than just estimating it. So the factors that affect the performance of our aeration system, first of all, alpha. Alpha is the ratio of the oxygen transfer coefficient in wastewater to the oxygen transfer coefficient in tap water. Beta is the ratio of the oxygen saturation concentration in wastewater versus the oxygen saturation concentration in tap water. We have to know these values. Typically, alpha is in the range of 0.8 to 0.9, and beta is typically in the range of 0.9 to 0.94 for municipal wastewater. And we have little or no control over alpha and beta in our wastewater. Now, the mixed liquor DO concentration is also another very important factor that impacts the energy efficiency of our aeration system. And that's the one where we have the greatest control. So it's very important that we try to operate at the DO concentration, the lowest acceptable DO concentration, because that's going to enhance the oxygen transfer efficiency. And typically in most activated sludge systems, we'll try to maintain a DO of 1 to 2 milligrams per liter. If we have high organic loading, we may need to increase the DO concentration to deal with high organic loading. But typically 1 to 2 milligrams per liter is adequate in our biological reactor where we have aerobic conditions. And the side elevation is also important. As we increase elevation, we're going to reduce the oxygen transfer efficiency of our aeration equipment. So again, recommended DO concentration, typically 1 to 2 milligrams per liter would be adequate for activated sludge in most scenarios. And as long as we're maintaining about 1 milligram per liter, that should be adequate to biologically oxidize ammonia to nitrite and to nitrate. And operating at any higher DO concentrations is going to reduce the oxygen transfer efficiency of our aeration system. And and we're going to need more energy to put oxygen into the wastewater. So it's very important that we control our operating DO concentration. Energy conservation measures for diffused aeration system. We want to properly size our blowers. Talk more about that later. That's usually in the design phase. I visited a treatment plant recently where they only had 2 700 horsepower blowers, and each one was designed for 100% of the aeration capacity of the plant. And that gave us very little flexibility. So that's not an ideal design. Now, certainly 2 700 horsepower blowers when that plant was built it would have been cheaper to put in instead of say 4 350 horsepower blowers. But if you look at the life cycle costs and the flexibility that would have been afforded by using 4 350 horsepower blowers in the original design, the life cycle costs of the aeration would have been much less, because we have, with the greater flexibility of having 4 350 horsepower blowers, again, we can make our aeration system operate much more efficiently than with 2 700 horsepower blowers. And then sometimes we can use intermittent aeration, turning blowers on and off. That's not always ideal, but occasionally can be done. A better way is to provide a DO control system where we actually control possibly the speed of the blowers, the settings of the intake vanes going into the blowers, and the diffusers on the outlet side of the blower. So we'll talk more about that later. So typically, blower systems should be designed for a downturn ratio of about 5 to 1. And again, we've got to design the blowers for the ultimate oxygen demand of our design, but we may, again, only be operating at 20, 30, 40% of design capacity when we start up the plant. So that's why we need a range of capacity. So typically, one design will be to design 4 blowers, each one being able to deliver 33% of the air required at design loading. So that way, if one blower goes out, we still are able to supply 100% of the air that's needed for the design loading. Another approach is to design two blowers at 25% of the air requirements at design loading, and 2 blowers at 50% of the air requirements at design loading. And either of those designs, 4 blowers at 33%, or 2 blowers at 25%, 2 blowers at 50%, if either one of those designs, if one blower goes out, we still are able to supply the design air that's needed. All right, energy savings with blowers. Again, it may be cost effective to go in and actually replace a large blower with 1 or 2 or more smaller units. And another way to save energy is to install a variable frequency drive on the blower. That may not be a good idea for centrifugal blowers. Some centrifugal blowers are not ideally suited for variable frequency drive, so we have to be careful about saying, hey, let's just put a variable frequency drive on our blower and it's going to be effective for us. That may not always be the case. Use inlet throttling to control the output of the blower. And then another thing is we can install a DO control system where we try to maintain a set point DO in our aeration basin, and we'll control blower speed possibly along with inlet vane control and adjust that. And that will be adjusted based on the DO that's being observed in the aeration basin. A better way to do it for a diffused air system is to provide a DO control system that tries to maintain a reasonable DO concentration in the reactor, while at the same time trying to operate the blower near its best operating efficiency point. And so for a diffused air system, that would be our preferred DO control system, maintaining DO at a good level and also keeping the blower operating near its best efficiency point. An example here where one particular wastewater treatment plant, the design flow rate average daily was 18.5 million gallons a day. Currently, the flow rate was 10 to 12 million gallons per day. The organic loading was much lower than design loading. The plant had 5 700 horsepower blowers. With only one 700 horsepower blower operating, the DO in the aeration basins was in the range of 4.5 to 8 milligrams per liter, so much too high, which dramatically reduced the oxygen efficiency of the aeration system. So what we did in this, or what was done in this particular case, is two 700 horsepower blowers were replaced with two 350 horsepower blowers. And another thing, because the plant was so underloaded organically, they took 6 of the aeration basins out of service and went to 3 aeration basins. And their total energy savings was 1 million kilowatt hours per year. Their energy cost savings was $67,000 per year. The total cost of putting in these two 350 horsepower blowers was $200,000. So the payback was about 3 years, and this turned out to be quite effective and made the aeration system much more efficient. Let's talk about mechanical surface aerators, common types. We have low speed mechanical or surface aerators. We have high speed mechanical surface aerators. Brief comment here, low speed mechanical aerators are going to be about 20%, 20 to 25% more efficient than high-speed surface aerators. So a low-speed mechanical aerator, surface aerator, it'll operate through a gear reducer. The motor may be operating at 1700 RPM, but we operate through a set of gear reducers, and the blade on the aerator itself that's mixing the water and imparting oxygen transfer to the water may be only turning at 60 to 80 RPM. But direct drive or high-speed surface aerators, the motor's operating at about 1700 RPM, and the blade on the aerator or impeller is operating at 1700 RPM. We have horizontal rotor aerators. Instead of a vertical axis like the first two, we have a horizontal axis. We'll talk a little bit more about them. We have aspirating aerators, and we also have Orbal disc aerators, and there are other types, but these are the 5 common types of surface aerators that we would use in activated sludge processes. This is an illustration of a slow speed vertical aerator in an activated sludge treatment plant. Again, very efficient in terms of oxygen transfer. Here we have a cutaway view of a high-speed surface aerator. Again, the impeller will be turning at the same speed as the motor, and so very high speed, and they're, again, about 20% less efficient than a slow-speed surface aerator. Fixed horizontal surface aerators or approximately equal to a high-speed surface aerator, and we'll talk about transfer rates in a little while, but these are typically used in oxidation ditches. We can also use floating horizontal rotor aerators. They can be used to replace fixed rotor aerators that have failed. And the nice thing about the floating horizontal rotor aerators, they can be placed in the ditch in a few hours of time without actually taking the ditch out of service. And you see a picture of a horizontal rotor aerator here. Again, they're supported with floats, and they operate usually at the optimum setting as far as the submergence of the blades inside the biological reactor. And these units typically can be purchased in horsepowers ranging from about 5 horsepower up to about 30 horsepower. Have circular disc aerators, also called Orbal aerators, typically used in Orbal oxidation ditches, and they, again, in some cases, they'll be used to replace fixed blade rotors in a conventional oxidation ditch, but these are known again as Orbal or circular disc aerators. Aspirating aerators, they're located on pontoons and float in the mixed liquor, and they will again aspirate air. And look at a little different picture here. What we have is an air intake port right here. It's where the air is pulled in. We'll go through an horizontal, a shaft, a hollow shaft that's got air slots. And then we have a specially designed stainless steel propeller down at the end. And so the air is aspirated into this hollow shaft, and the propeller disperses it into the mixed liquor. So how do we measure performance of surface aerators? We use, for diffused air, oxygen transfer efficiency, but for surface aerators, we call it oxygen transfer rate. So aerator manufacturers, they will measure the standard oxygen transfer rate of their equipment and report that. That will generally be provided in their literature. And again, the standard oxygen transfer rate will be at tap water, 20 degrees C, initial DO of 0.0 milligram per liter and 1 atmosphere of pressure. And that will be expressed in pounds per horsepower hour. The field oxygen transfer rate is what we want to calculate. We have to translate, again, from the standard oxygen transfer rate to the field oxygen transfer rate, because we want to know what that aerator will do in at field conditions. And again, for surface aerators, it'll be expressed in pounds per horsepower hour. As we said before, these are the factors that affect the performance of the aeration equipment. So I'm showing those again: alpha, beta, mixed liquor DO, mixed liquor temperature, and site elevation. And of these 5 factors, the most important factor will be the operating DO concentration. The second most important factor will be the site elevation. Mixed liquor temperature is important, but if we're operating at an elevation of less than about 1,000 feet, and we're operating at a DO concentration of 1 to 2 milligrams per liter, the surface aerators are going to be only slightly less efficient in the summer than they are at winter temperatures. So we'll talk more about that in a moment. This equation that you see at the top, the field oxygen transfer rate of surface aerators will be the standard oxygen transfer rate times alpha times beta rho C sub S minus C sub S being the saturation concentration in tap water. And what beta does, it corrects it to wastewater, and rho is our elevation correction factor. So the driving force for oxygen transfer is the saturation value minus the actual concentration at which we're operating in our reactor. So we call that the driving force. So in this particular equation, there are 2 multipliers here. This multiplier inside the brackets, is the driving force. So it's the driving force of the difference between saturation and actual oxygen concentration. The greater that difference, the greater the oxygen transfer rate. So as we increase the temperature of the water, the saturation value is going to go down. So as we increase the temperature, this multiplier will go down. But there's another multiplier here in the equation, 1.024 raised to T, which is temperature in the mixed liquor, minus 20. So this multiplier, as the temperature goes up, what this says is the actual physical chemical transfer of the oxygen across the air film and the liquid film into bulk solution, that transfer rate will actually increase with increasing temperature. So we got competing factors here. Let me get back to my equation. So as temperature goes up, this multiplier goes up. As the temperature in the mixed liquor goes up, this multiplier goes down. So if we're operating at a DO of 1 to 2 milligram per liter and we're less than 1,000 feet elevation, these multipliers almost exactly cancel each other out, so that temperature under those conditions has very little impact on the overall transfer rate of the aeration equipment. So make sure you understand what I just said. If we're operating in a DO range of 1 to 2 milligrams per liter and we're at elevation of less than about 1,000 feet, the aeration equipment will typically be only 3 or 4% less efficient in the summer than it is in the winter, and that's a minor change. And if you're an engineer or an operator, you say, well, I know I have to operate a greater amount of horsepower in the summer than I do in winter. Well, the main reason for that is because mixed liquor temperature in the summer may be 28 degrees C. Mixed liquor temperature in the winter may be 10 or 12 degrees C. So during the summer, the endogenous respiration rate of the biomass is going to be much higher. And so you're going to need more oxygen supplied to the biomass in the summer because of what's happening in the mixed liquor biologically. So we need more oxygen in the summer, mainly because the biomass need more oxygen. It's not that the oxygen, the aeration equipment is dramatically less efficient in that 1 to 2 milligram per liter range. So let's look at this to illustrate what I'm talking about. Using the previous equation, the standard oxygen transfer rate for the aeration equipment is 3.0 pound per horsepower hour. We use alpha 0.84, beta 0.92. Again, we have little control over those values. Rho is 1. That means we're operating at an elevation less than 500 feet. And we're going to operate at 10 degrees C. Our saturation value in tap water is 11.33 milligram per liter. We're operating at a 2 milligram per liter DO concentration. So under those conditions, the actual field oxygen transfer rate will be 1.8 pounds per horsepower hour. All right, now we're going to go from winter to summer conditions. And now instead of the temperature being 10 degrees C in the mixed liquor, we're in the middle of August. And now our temperature in the mixed liquor is 30 degrees C. And how has our oxygen transfer rate? Alpha and beta stayed the same, rho stays the same, where we're going to maintain same DO, 2 milligram per liter at the same elevation. So the only thing we've changed is we've gone from a 10 degree temperature to a 30 degree temperature. Now the field oxygen transfer rate has dropped from 1.8 on the previous slide to 1.71 pounds per horsepower hour. So we have about a 5% drop in the oxygen transfer rate. That's a fairly minor drop in transfer rate for the surface aeration equipment. Now what we want to do is we're going to operate all things the same. We're in summer conditions, 30 degrees C, but now we're decided to operate at a DO concentration of 4 milligram per liter instead of 2 milligram per liter in our aeration basin. So because of that, our transfer efficiency has dropped from 1.71 pounds per horsepower hour now to 1.01 pounds per horsepower hour. So simply increasing the operating DO concentration from 2 milligram per liter to 4 milligram per liter, we have in effect reduced the efficiency of our aeration equipment about 40%. So that's why when we optimize our aeration system, we want to make sure that we operate at as low a DO concentration as possible, because that's going to enhance the efficiency of our aeration equipment. Again, too much DO not only reduces the efficiency of the aeration equipment, it may over-oxidize our biomass and contribute to poor settling in the final clarifier, may increase the amount of foam in our basin. And then if we have a high concentration of DO in our aerobic reactor and we're recirculating some of that mixed liquor back to our pre-anoxic reactor, then we're going to be sending too much DO back to the anoxic reactor. As far as approximate field oxygen transfer rates, we'll make some assumptions here. Alpha 0.84, beta 0.92, row 1, operating DO 2 milligram per liter without an elevation of less than 500 feet. So again, what we can do is we can take the standard oxygen transfer rate, multiply it by about 0.6 to estimate what our field transfer rate of these surface aerators will be. So for pump type aerators, vertical axis aerators, donut aerators, whatever you want to call them, the field oxygen transfer rate will typically be in the range of 1.4 to 2.3. The high-speed aerators will be in the lower range and the low-speed aerators will be in the upper end of the range. Horizontal rotor aerators, again, approximate field oxygen transfer rate for these conditions, about 1.4 to 1.8 pounds per horsepower hour. Orbital disc aerators, 1.3 to 1.5, and aspirating aerators, about 1.0 to 1.3 pounds per horsepower hour. Then let's compare that to our diffused air systems. And again, typically in diffused air systems, we define aerator performance in terms of oxygen transfer efficiency. But what I've done so that we're comparing apples to apples instead of apples to oranges. So if we compare oxygen transfer rate in pound per horsepower hour to oxygen transfer efficiency in percent, we can't make a comparison. So what I've done is made a number of assumptions here. Elevation less than 500 feet, the compressor efficiency of our blower 75%, tank depth 15 feet, and the diffusers located about 1.5 feet off the tank bottom. And with these assumptions, what I've done is I've calculated what would, translating the oxygen transfer efficiency for diffused air systems, I've now translated that into a pound per horsepower hour number so that we can compare it to our surface aerators. So for the non-porous, or what we might call coarse bubble diffusers, the field oxygen transfer rate will be about 1 to 1.5 pounds per horsepower hour. And for porous diffusers, it'll typically be in the range of about 1.5 to 2.3 pounds per horsepower hour. So I only did that so that we can make an apples to apples comparison of surface aerators to diffused aeration systems. So energy conservation measures for surface aerators, adjusting the submergence on the blades, using low speed aerators instead of high speed aerators. They'll generally be about 20 to 25% more efficient. We can turn the aerators off a few hours a day. This is especially useful in extended aeration activated sludge systems where we have nitrate, and we can turn the aerators off a few hours a day and allow the mixed liquor to go into the anoxic mode. And then again, we want to operate at the lowest acceptable DO concentration. Intermittent aeration, again, turning aerators on and off may not be appropriate for all facilities, but again, in extended aeration facilities where we're nitrifying, we got a lot of nitrates, we can save energy by turning off the aerators a few hours a day without adversely affecting the performance of the activated sludge process. And then installing a DO control system so that aerators, or the speed of the aerators may be controlled, or we'll turn aerators on and off depending upon the set point DO concentration in the mixed liquor. So automated DO control is again, a very useful way And many, I would say now, probably as many as half of activated sludge plants have an automated DO control system because they realize the value of it. We're going to control our aeration equipment as efficiently as possible and to match our oxygen supplied with the oxygen required. So we're going to optimize our aeration system. And another thing we need to recognize is during the middle of the night, our aeration requirements usually fall. Aeration requirements during the night may only be 60% or 70% of what they are during the day. So again, we want to be able to use our DO control system so that we control our aeration equipment and supply only the amount of oxygen that we need. If we put in a DO control system, we can usually save 10 to 30% on our energy costs. Obviously, the energy savings is going to depend upon the conditions at a particular wastewater treatment plant, because elevation is important, and other factors, type of aeration equipment that we have, other factors will control it. But typically, if we put in an automated DO control system, we can save 10 to 30% on our energy costs. So if we put in a DO control system, our payback typically will be in a matter of 2 or 3 years. So that's a brief run through of aeration systems. So if that gives you a better idea of aeration systems and how we can control those to make them more cost efficient and save energy. And hopefully if you go out and evaluate a treatment plant, you've got some tools now to determine how you can help them save energy in the aeration system. You see my contact information as well as Tom Winning at Oak Ridge National Labs. Thanks for listening. Hope you have a great day.